Well, I mean, the short answer is we don't know. And I talked to different people when I was researching this book, and I had the privilege to chat with Roger Penrose for a couple of hours at his office in Oxford. But just to summarize, he says, I don't think the arrow of time is going to be explained by just waving the second law around. It's much more subtle. And he spent quite a large number of years contemplating these things. So I'll leave that alone for now and talk a bit about Einstein, because we do have some stuff to get through here. We'll have to talk about Einstein if we're going to talk about the nature of time. I'm not going to attempt to sort of give an overview of how relativity works, but I will talk about some of the implications of it. Very briefly, the two parts of Einstein's theory, special and general relativity, are refinements of Newton's laws. Special relativity gives you a new set of laws of motion and how things are going to behave when high speeds are involved, speeds that are close to the speed of light. General relativity goes beyond that. General relativity is a theory of gravity. It shows a link between gravity and the actual geometry of space and time themselves. And together they give us a whole new view of space and time. So, as I said, I'm going to focus on some of the impacts or repercussions of Einstein's theory. This is a partial list of some things that you have to get used to in Einstein's world. Space and time are linked. We can call this new structure space-time, and I'll talk a little bit more about that in a moment. Time measurements depend on speed. This seems very counterintuitive. In Newton's world, time is just time, right? It was absolute. It really didn't matter whether you were moving along quickly or slowly or whatever. But in Einstein's world, which is the world we live in, of course, it is more subtle. And if I was moving along here really quickly, you would think my watch was running slow. And if I was looking out at you guys and you were wearing your watches, I would think your watches were running slow. And basically, we would both be right. Twins can end up with different ages. This seems bizarre, but it's true. If I had an identical twin and the twin sort of ran away at a high speed, turned around, that's the crucial part, turned around and came back, at the end of this ordeal, the twin would be just a little bit younger. And I will talk a little bit more about that later when we get to the really fun stuff about time travel and what would happen if you accidentally run over your grandfather with your DeLorean during your trip into the past. Gravity distorts space-time. That's important too, and we'll have a little bit more to say about that later on. But let's start with this question of how do we picture four-dimensional space-time? Some of you who have already read different books, or maybe read Brian Greene's Fabric of the Cosmos, or watched that three-part series on PBS they did of his first book, Elegant Universe, sort of already know all this stuff. But it's fun to go over. Of course, you can't picture four-dimensional anything, but you can use little tricks. And the best trick of all is to strip away one of the dimensions. Now you only have to picture something three-dimensional. And if the thing you're interested in only has, normally the space around us we think of as being three-dimensional. But if you look at a very simple system like the Earth going around the Sun, the interesting stuff really only happens in two dimensions anyway, because it's just a circle, a frisbee-like sort of thing, and the Earth goes around the Sun, and there you go. So even though when you're in junior high school or high school, and they give you these, you start doing stuff about space, and you give the X, Y, and Z axes, and so on, we really only need X and Y. So as you can see, and some of you know exactly what's coming, we've saved the Z-axis. We can pretend that the Z-axis is time, and now we can sort of imagine how this simple physical system evolves in time. And of course, the circle becomes a helix as the Earth goes around and around the Sun, but also time is going forward. This is a useful tool. I guess the question we might want to keep at the back of our minds is, are you allowed to do this? Are we cheating? If we are, it might not be any worse than the trick we did with the number line and the arrow a little bit earlier. I pretended that time was just like space. And this diagram makes it look like time is just like space. So this is tricky. The thing is, of course, time is a little bit like space. But the question is time really, really like space? And that's something to ponder. Well, physicists draw these diagrams, then it's good to give names to the components, the world line of each of these two objects. The sun, if we choose a reference frame where the sun is just sitting there, then the world line of the sun is just a straight line that goes up the center of the helix. The world line of the Earth, of course, is this helical pattern. And you have a world line, and I have a world line. Mine starts in Halifax a certain number of decades ago, and yours starts somewhere. And I suppose our world lines will end when we die, although the atoms, the world line of the atoms, I suppose, will keep going. So this is a way of sort of imagining the universe as trying to take time and picture it just like you would the other dimensions. Well, there may be some peril in doing that, but nonetheless, it's probably at the very least a useful kind of trick. Going back to the implications of Einstein's theory, and this is one of the big ones. There's no absolute simultaneity, no universal now. Now, of course, in Newton's description of the world, we all share the same time because time is just there. There's sort of like a master clock for the universe. And if there are two events like this, well, those were more or less simultaneous, whatever. But in Newton's world, they either were or they were not. In Einstein's world, there can be disagreement. It's a bit shocking, really. Different observers can disagree as to whether event A and event B are simultaneous or not. And this is a little tricky. I try to illustrate it as best I can. Einstein was very good at dreaming up these thought experiments. I mean, in fact, he was the master of it. And in Einstein's day, of course, the things that went by really quickly were trains, so a lot of his thought experiments involved trains. And I've just sort of juiced it up a little, but the ideas here go right back to Einstein's initial work on special relativity. So we have a person standing in the middle of a train car, and he's holding something like a modern electronic flash unit, let's say. And when he pushes the button, photons of light go off to the left and to the right. And just for fun, I put photodetectors at A and B, on the left-hand side and the right-hand side of the train car, in such a way that when the light hits the photodetectors, it'll trigger them to flash. So what will happen in a few nanoseconds is that A and B will flash. Okay. And your friend is watching from the platform. Well, from your viewpoint inside the car, of course, the beam of light goes off to the left, reaches A, goes off to the right, and reaches B. And that's it. A and B are simultaneous. The train isn't moving yet. So you say A and B are simultaneous, and your friend says A and B are simultaneous. That's fine. We put the train in motion with a very high speed, close to the speed of light. The letter C is just the symbol that physicists use for the speed of light. Well, now, the beam of light doesn't have as far to go to the left.